Good afternoon. My name is Caroline Trippel, and I'm a new assistant professor in the Computer Science and Electrical Engineering departments. Today, I'm going to give an overview of my work on leveraging formal methods techniques to evaluate the ability of hardware systems to reliably and securely execute applications. Optimizing for high performance in power-efficient hardware organizations has led to pervasive heterogeneity and parallelism in modern hardware systems. This slide features some Apple iPhone architectures as an example, each with dozens of specialized hardware components that operate and interact concurrently. Unfortunately, what heterogeneous parallelism buys us in terms of power and performance comes at the cost of increased design complexity, with each of these different hardware modules being programmed differently and interacting through shared system resources differently. This complexity makes it difficult to reason about the ways in which hardware systems implementations can potentially negatively impact the correctness and security of programs that run on them. In particular, the complexity of modern hardware systems, coupled with a lack of tools for comprehensively evaluating correctness and security as hardware design metrics, has resulted in real-world hardware bugs that affect the correctness and security of real programs. This slide features some recent examples, some of which were found by tools and techniques I've developed in my work, which are highlighted in red. Taking a closer look at security, which will be the primary focus of this talk, hardware security is clearly an issue that is gaining traction in both the architecture and security communities. These plots show that at 4 top architecture conferences and 3 top security conferences over the past 5 years, the number of published hardware security papers has been steadily increasing. If we take a deeper look at the type of research being conducted at these venues, there's an emphasis on defense research in the architecture community and an emphasis on attack research in the security community. However, many of the proposed defenses and attacks lack rigorous mathematical analysis techniques. This can lead to inadequate defenses or even incremental attack discovery. Moreover, attack development in the security community largely involves commercial hardware designs where mitigations are expensive, if not impossible. Furthermore, only about 19% of hardware security research over the past 5 years can be categorized as verification research, where verification here includes heuristic and testing-based techniques. My research aims to fill this gap. In particular, my research aims to promote correctness and security as first-order computer architecture design metrics, like performance and power. To achieve this goal, my research can be partitioned into a couple major themes. The first theme deals with developing tools and techniques for verifying the correctness and security of hardware systems. This work has led so far to the discovery of a series of bugs in the RISC-V memory consistency model, as well as the C11 memory model and some commercial compilers. It has also resulted in automatically synthesized new variants of the now famous meltdown inspector attacks. Since verification requires some property to verify against, the second major theme of my work deals with developing formal interface specifications for describing correctness and security guarantees throughout the hardware-software stack. So, how exactly can hardware introduce correctness or security bugs into a seemingly correct and secure program? As a basis for thinking about this problem, let's consider this small parallel C program. Thread 1 is initializing some data and setting an init variable equal to true. Thread 2 is then going to use this data only if it observes that init has been set equal to true. As this program is written, it might seem reasonable, but it could actually result in an uninitialized use of data, leading to incorrect or unintended program behavior, or even security vulnerabilities. This is because some compiler or hardware optimizations may elect to reorder the instructions on each of these threads in an effort to improve performance of the overall program. Since instructions on each of these threads are operating on distinct memory locations. To fix this program, we can declare init as an atomic variable, which essentially informs the compiler that init might be accessed by multiple threads, and therefore memory accesses to init should not be reordered with other memory accesses in the program. So with certain language level annotations like atomic, the programmer is able to communicate to the compiler what the ordering requirements are for a program's memory operations. This set of rules that assign different ordering semantics to different types of program memory operations is referred to as the memory consistency model of the programming language, abbreviated as MCM in this presentation. In order to translate this program into assembly code, the compiler also needs information about the features of the target hardware. This information is supplied in the instruction set architecture, or the ISA, which contains a couple primary components. The first, somewhat obvious component is the instruction interface that defines what instructions are in the hardware's assembly language and how they access and update processor state. From just this information, we could translate the program into assembly equivalent instructions by abiding by this ordering requirement of the program that we're not going to reorder accesses to init. The second key component of the ISA is a memory consistency model, which specifies the ordering guarantees of the hardware. So for example, if the ISA memory model specifies that stores to different addresses and loads to different addresses may be reordered by the hardware, the compiler will insert special fence or barrier instructions to explicitly prohibit instruction reorderings as the program requires. So now we have this program, which for the sake of this example, let's assume we know it is correct and secure. And let's assume that we've compiled the program in a way that has preserved all of the correctness and security properties of the original program. Unfortunately, even though we've made it this far, this program can still exhibit correctness or security bugs when it executes on hardware. The reason for this is that when this program runs on hardware, individual instructions do not execute atomically. Instead, they execute as a series of steps. Effectively, each instruction gets cracked into a series of hardware-level events. The events corresponding to one instruction can interact with the events corresponding to other instructions in the program in a variety of different ways during the program's execution. And some of these event interactions might ultimately translate to program-level correctness or security violations. All of these possible hardware event orderings and interleavings that may take place during a program's execution on a particular hardware implementation correspond to a variety of different ways in which the program could execute. So if we want to be able to say that a program will always execute in a way that is correct and secure, we need the ability to effectively analyze all of the different ways in which the program could execute on a given hardware design so that we can check them for correctness and security violations. Fortunately, the field of automated reasoning has produced powerful tools and techniques that we can leverage in order to achieve our goal of searching the space of possible program executions for those which exhibit program correctness or security bugs. However, the challenge in using these tools is that we first need to come up with a description of the system being evaluated that a computer can understand. In other words, we need to come up with a formalization of the system being evaluated. We additionally need to formalize a correctness or security property to evaluate. Once we have supplied both of these inputs, we can then ask an automated reasoning tool, such as a SMT or SAT solver, to find us a witness to or a counterexample to our specified property. Ideally, we'd like to automate as much of this process as possible, particularly the formalization process, both for usability and to prevent errors in the formalization process. So going back to our program example from before, where we have a store to data, a data variable, followed by a store to an init flag on core 0, and then a load of this init flag followed by a load of the data on core 1, we want to determine if the illegal correctness property at the bottom of the program can ever be violated when the program runs on this pedagogical 5-stage out-of-order pipeline processor design. This property corresponds to the case where core 1 observes the init flag has been set, yet observes stale data. To achieve this, we will formalize hardware-specific program executions as directed graphs called microarchitectural happens before graphs, or MUHB graphs. The graph on the right-hand side of the slide is a MUHB graph. It represents a specific execution of the program of interest on the hardware design that corresponds to the illegal property of interest. Looking at the graph in more detail, row labels correspond to hardware locations of interest within the design. Column labels correspond to instructions in the program that's currently executing, with instruction sequencing from left to right on each of the constituent cores. MUHB nodes correspond to microarchitectural events that take place during the program's execution. This particular node represents the event corresponding to the store of one into data, updating some state in a local store buffer. Edges correspond to logical happens before relationships between events. This particular edge represents the idea that the store of one into data is fetched from instruction memory before the store of one into a init is fetched from instruction memory. This edge represents the concept that this processor features an in-order fetch stage. Some edges, like this one, are instruction agnostic, meaning that this processor, for example, has an in-order fetch stage regardless of whether it's fetching loads or stores or branches. Other edges, like this one, are not instruction agnostic, and rather they represent data flow relationships in the processor. For example, this particular data flow relationship this particular happens before edge is representative of a data flow relationship between the store of one into a init on core 0 and the load of a init that returns the value 1 on core 1. In particular, since the memory hierarchy is the only mechanism by which two distinct cores can communicate with each other, the only mechanism of shared state between the cores, the load of 1 into a init must have happened after the store of 1 into a init reached the memory hierarchy. What makes happens before graphs like this MUHB graph so useful for evaluating correctness properties like the one on this slide is that a cycle in a happens before graph corresponds to an impossible or unobservable event sequence, while an acyclic graph corresponds to an execution scenario that is possible or potentially observable. Here, the graph is acyclic, meaning that the illegal program behavior is observable on this hardware design. If we wanted to forbid this behavior in hardware, we could do so by changing the design in a way that orders the execution of loads. This would add a new edge, the new red edge, to the happens before graph and render the execution unobservable, as illustrated by the presence of a cycle highlighted in red. Going back to our goal from the previous slide of formalizing the search for hardware-specific program executions that can violate program correctness or security properties, we can formally specify our hardware design axiomatically in first-order logic. So this is the formalization of our system. We can formalize our property as an acyclic UHB graph that corresponds to the illegal outcome we are evaluating. And finally, we can use automated reasoning tools like SMT or SAT solvers to find a witness to the property like the acyclic graph on this slide. One way in which I've used MUHB graphs in my work is to verify that a given high-level language memory model, ISA memory model, compiler mappings from the high-level language memory model primitives to the ISA memory model primitives, and finally hardware implementation of the ISA all align on memory model requirements. In particular, we wanted to provide hardware designers with a tool to conduct early-stage analysis of their proposed designs with respect to high-level language programs that they intend to support. The goal is to catch hardware incompatibility bugs early in the design process. To do this, we evaluated and developed a tool called TriCheck, which begins with a suite of automatically generated high-level language litmus test programs, where a litmus test program is a small parallel test program like the one you saw on the previous slide that are designed to localize verification to the places most likely to exhibit bugs. Then from this suite, TriCheck will generate a corresponding suite of assembly language litmus test programs and leverage MUHB graphs to ensure that the high-level language correctness requirements are always preserved when the programs are compiled and run on the microarchitecture in question. So in the MUHB graph example and in TriCheck, the properties we were trying to evaluate are correctness properties. Since program correctness involves correctness of software observable program state, these correctness properties were defined in terms of the architectural state of the program. MuHB graphs were then used to analyze hardware executions capable of producing particular architectural behaviors. On the other hand, security properties may involve state that is not architecturally visible, but rather is simply detectable, for example, via a simple side channel attack. In order to support security modeling and verification with the MuHB graph formalism, we developed the checkmate approach, which augments the MuHB modeling paradigm with a new feature. Specifically, we propose MuHB patterns as MuHB subgraphs, which correspond to a particular combination of hardware events and any relevant orderings between them. When a MuHB pattern is indicative of some class of exploits, we call it an exploit pattern. The checkmate approach is based on the idea that if we can formalize classes of security exploits as MuHB exploit patterns, and if we can formalize hardware-specific program executions as directed graphs, then a MuHB graph that features an exploit pattern represents an exploit program execution and a witness to an exploit pattern security property. Given our new mechanism for formally specifying security properties as exploit patterns and our existing technique for formally specifying the hardware system we are analyzing as a first-order logic axiomatic model, we designed the checkmate tool. Checkmate conducts hardware-aware exploit program synthesis given the hardware system formalization and an exploit pattern formalization provided in the same first-order logic format. The techniques I've discussed so far, including try-check and checkmate, have identified correctness and security bugs in real-world processors and compilers. For example, we identified a series of deficiencies in the 2016 version of the RISC-V memory model specification, which have since been fixed, and 2 new variants of the now famous Meltdown Inspector attacks, which rely on different microarchitectural mechanisms for leaking information, specifically the cache coherence protocol. More broadly, my work has looked at applying formal methods techniques to various correctness and security problems throughout the hardware-software stack. I want to wrap up with a couple current research directions that I'm currently pursuing that build on the work I've discussed so far. The first project involves improving the scalability of Checkmate. Checkmate was able to discover real bugs that affect real processor designs. However, improving its scalability and usability involve 3 main research challenges. First, Checkmate currently relies on designer-provided formal specifications of hardware. We are now working on developing techniques for extracting these formal specifications directly from RTL with the help of intermediate data flow graph representations and bounded model checking. Next, Checkmate requires the input hardware design to be provided as a monolithic processor description rather as a collection of hardware modules. So our second goal is to adapt the Checkmate algorithm to conduct modular and hierarchical security verification. Finally, Checkmate's current implementation suffers from inefficiencies that result from a naive encoding of our security verification problem in SAT. We believe we can exploit domain-specific knowledge to benefit from SMT and symmetry breaking strategies. The second project involves specifying security models to facilitate formal security reasoning throughout the hardware-software stack. Consider the program on the left-hand side of the slide. This program is a compact representation of a prime and probe cache side channel attack that could be synthesized by Checkmate. Formally specified memory consistency models place constraints on shared memory interactions that can take place between memory operations in a program. For this program, memory model formalisms would establish a reads from, denoted by the RF edge, relationship between the write of 1 to A1 and the read of 1 that returns the written value. However, there is no apparent interaction between thread 0 and thread 1 from only considering plausible memory consistency model interactions. The goal of formally specifying security models is to facilitate reasoning about when information leakage is possible in programs by defining the legal interactions that can take place between instructions via microarchitectural state. For example, the new COM-X edges that signify microarchitectural state interactions between the 3 instructions in this program, which share some common hardware state, X as 0, which could theoretically be represented by a shared cache line, now enable us to reason about the potential for information leakage in this program. Formally specifying security models can enable hardware security verification, secure compilation, and even potentially secure hardware synthesis. The tools I discussed today are open source and can be found via my webpage. Thank you for your attention, and I'm happy to take any questions.